Hey guys, in this video we're going to talk about Chapter 1, Section 4, Functions and Change. So to introduce this topic, I want to give you a scenario and, what we're interested, especially with real-world scenarios, is how things change over time, right? Things can change rapidly over time, or they can change slowly over time, or they don't have to change at all over time. And we're going to be focused on those sorts of questions in today's lecture. All right, so here's the situation. You start with $500 in your savings account. After a month, you have $700, so you save $200 in a month. And then you start to record how much you have after M months below. So we're letting M be our independent variable here. Now, usually when we talk about independent variables, and we're talking about time is going to be the independent variable pretty much all of the time. So, okay, so here's what our little table says. After 0 months, we have $500 in our savings. After 1 month, we have $700. After 2 months, we have $800. 3 months, we have $1,200. And 4 months, we have $1,400 in our savings account. So what we're interested in this situation is how our savings grows over time. Does it grow at a constant rate over time? Or does the way that it grows change over time? Well, what we can do is we can look at this in the table format, or we can look at it on a graph. So I graphed this stuff in Desmos. Now our ordered pairs, we have our time as our independent X variable, so that comes first, and how much is in our savings at that time is the second number in the ordered pair, our Y value. So we can examine, what's happening over time by connecting successive dots. So what I mean by successive is the one that comes right after the next. So for instance, between month 0 and month 1, I can connect those dots, and it makes a line segment, right? And then what I can do is I can look at the next pair. So between 1 and 2, I can connect those dots. And then between 2 and 3, I can connect those dots. Between 3 and 4, I can connect these dots. Okay? And the way that I'm going to analyze this is by looking at how steep that connecting line is, right? So where is the connecting, which connecting line is the steepest? Look at these. We have 1, 2, 3, 4 connecting lines, and what I want to know is which one is the steepest. Well, the one that's the steepest, what would be hardest to climb up if you had to climb these things would be this one. This is the steepest. And what this corresponds to, this line segment being the steepest, it means that the change that's happening is the greatest. So this is the greatest change. This is the greatest increase in change, the greatest growth. Okay, so this is the greatest change, is where the steepest line segment is. And it makes sense, right? Because from month 2 to month 3, we're increasing from $800 to $1,200. So that's an increase of $400. Whereas between month 0 and month 1, if we're going from $500 to $700, we're increasing by $200, right? Between month 1 and month 2, we're increasing by $100. 2 and 3, we just said, was increasing by $400, and between month 3 and month 4, we're increasing by $200. So it makes sense that this is the steepest because it's the greatest increase. Now, which one is going to be the flattest? The flattest line is going to be the smallest increase, which is between month 1 and month 2. We can see that right here on our little graph. We can see that this guy has the flattest line segment, and this is going to correspond to the smallest change, only $100. So what happened? I don't know. Something probably happened between month 1 and month 2. Maybe taxes were due or something. And this is still growth because we're still saving $100, but it's the smallest change between in a month. In a month, it's the smallest change. So that's what we're going to be interested in this lecture: how things change over time, and what we call the steepness of a line segment. We're going to refer to this as the average rate of change. Now, in the next video, or next week, we're going to be talking about average rate of change as slope. But in this lecture, we're going to refer to it as average rate of change. Just in the back of your head, you can think of this as slope if you want to. We're going to talk more about what slope means next week. But yeah, average rate of change is the measure of steepness of a line segment. All right, so let's go ahead and look at another example. So here we have a table given. Our independent variable is in months, so that's acting like our quote-unquote x value. It's t, it's our t variable. And we have month 0, month 3, 6, 9, and 12. And then we have our output variable is the population of a termite colony. Okay, so at month 0, we have 1,000 termites in this colony. At month 3, we have 2,500. Month 6, we have 4,000, and so forth and so forth. And so we're going to answer some questions to analyze this table a little bit more. We're concerned with how the population of termites changes. So part A says, how does it change from month 0 to month 3? How does the population change from month 0 to month 3? Well, we just kind of see what happens with the population here. We're going from 1,000 to 2,500. If we subtract 2,500 minus 1,000, well, that's a net result of 1,500. So from month 0 to month 3, it changes 1,500, and it's a positive change, right? It increases, that population increases. What about from month 3 to month 6? All right, so again, we're just going to look at the difference in population from month 3 to month 6. We're increasing, right? We're going from 2,500 to 4,000. So we're going to be doing the difference between 4,000 and 2,500. And 4,000 minus 2,000 is 2,000. So minus 500 more is 1,500 again. So again, this is a net change of 1,500. So it's the rate of change is constant. We would say that between these two sets of months. And then if we look at month 6 to month 9, well, now we're going from 4,000 to 7,000. So 7,000 minus 4,000 is going to give us 3,000. So that's a net result of positive 3,000 is what we're increasing by. So the change is not constant here. We're increasing by quite a lot. Maybe it's during the summer months or something. I don't know when termites get really bad in Louisiana. I don't think they do in New Mexico though. I'm not sure. But anyway, maybe it's termite season now from month 6 to month 9. Okay, what about from month 9 to month 12? So we're going from 7,000 to 2,800. All right, so what's the difference between 2,800 and 7,000? Well, this time we're getting a negative difference, right? If we do this, 2,800 minus 7,000, we get a net result of negative 4,200. So we decreased a bunch. I don't know why. Maybe the exterminator came out. You could think of your own little story, to go with this situation. But the point is that At month 9, we had 7,000 in our population, and at month 12, we have 2,800. So I'm guessing the exterminator might have came and sprayed. But anyway, this is how you can get a little story from this table to see how the population is changing. All right, so now we're going to get into we're going to look at the math in terms of, basically what I'm trying to say here is in this first situation, it was kind of easy for us to see how things were changing because the time that we were given was changing by 1 each time. Like month 0 to month 1, month 1 to month 2, month 2 to month 3. It was easy to see what was happening because the change was in equal increments of 1 for our time. And same thing with our termite population. We were changing in increments of 3, right? 3 months. But sometimes we're not going to be given that. And to handle that, we have to use a formula to figure out, basically, we're looking, this formula that we're using is going to tell us the change per unit of time, per 1 unit of time, okay? And it's going to make more sense as we go on, but that's what we're going to be doing. So this is called the average rate of change. Now, in the back of your head, you don't have to know this word yet, but next week we're going to be talking about average rate of change in terms of slope. And all this means, again, this is just the measure of steepness of a line segment, just like we did in the first example. It's just a measure of steepness. All right, and so this is how we calculate it. There's 3 different ways of looking at it, but basically you're just doing your final output minus your initial output, so y minus y, over your final input minus your initial input, x minus x. So sometimes we call this the change in y over the change in x. This little symbol is a delta. That means the change, and maybe I'll write this here. Change in y over change in x. Okay, so that's the second way of looking at it. And then we just talked about function notation. So, this is our final output minus our initial output over our final input minus our initial input. You can look, if you're more of a graphical kind of guy or girl, you can look at this in terms of a graph. So like here's our initial input. Here is our final input. Here is our initial input, and here is our final input. So this would be, if I wrote this as an ordered pair, we could write it as A, comma, f of A for that first point right there. And the second point right here could be B, comma, f of B, if you want to look at it like that. We're going to do plenty of examples with this, so just know output minus output over input minus input is how we're going to measure the steepness of a line segment. So let's do some examples. So let's go ahead and find the average rate of change between t equals 0 and t equals 3. So this is our initial value. I'm going to call it A. So A equals 0. Now, we're thinking of t as our x's, our inputs, if you like that. So our initial value here is A equals 0. So you can think of this as our starting value. And our ending value, t equals 3, is our B. So this is our ending value right here. And then you just want to look at the corresponding outputs. So f of A is going to be the output of A. So the output of 0 is 1,000. And our output of B, our output that goes with B, is 2,500. So f of B is going to be 2,500. And then we're just going to use our formula. So we're going to use final output minus initial. So I'm doing output minus output. So f of B minus f of A. divided by B, which is 3, minus A, which is 0. Okay? And this is our population of termites. So, the output is termites, and the input is months. So on top, we know that our units are going to be termites, and the bottom, the units are going to be months. So on top, 2,500 minus 1,000 is going to be 1,500 termites. On the bottom, 3 minus 0 is 3, and that unit is in months. So 1,500 termites per 3 months. We're going to go ahead and simplify this. 1,500 divided by 3 is 500 termites per 1 month. You see how we got this in unit of time, 1 month. So again, 1,500 divided by 3. 3 goes into itself once. 1,500 goes into, or 3 goes into 1,500 500 times. So 500 termites per month is the average rate of change between t equals 0 and t equals 3. So that's our answer here for number 1. So this is the average rate of change right here. So let's look at the next unit of time. So now we want to find the average rate of change between time equals 9 months and time equals 12 months. So again, we're just going to label A and B like we did in number 1, and f of A and f of B. Alright, so our beginning time is t equals 9, so A is going to equal 9. And the corresponding output, f of A, well, if we look at our table, and I already circled this because I had to edit the video just a second ago. But anyway, when A is 9, our corresponding output is 7,000 termites. So f of A is going to be 7,000. And then for B, our ending time is time equals 12 months. And our corresponding f of B is going to be 2,800 termites. So if we use our average rate of change formula, we have f of B, which is 2,800 termites, minus f of A, which is 7,000 termites, all divided by B, which is 12 months, minus A, which is month 9. Okay? Alright, so then if we do 2,800 minus 7,000, we're going to get negative 4,200 termites on top. And let me just erase some of this to get it out of the way so we have a little bit more room. So we have negative 4,200 termites on top. And on bottom, 12 minus 9 is 3 months. Can I simplify this any more? Let's see. Yeah. So 4,200 divided by 3. 3 goes into itself once, and it goes in a negative 4,200, negative 1,400 times. So here our average rate of change is negative 1,400 termites per month. So that's how we measure the steepness of the line segment that connects these 2 points right here, this point and this point. The steepness is negative 1,400 termites per month. So we're losing termites in this span. Let's try this one. So between t equals 0 and t equals 12. So now we're connecting the line segment that goes from this point right here to this point right here. Okay? And if you want to, you can put this in Desmos. Now, how do you put this in Desmos? Well, you would go to the Desmos Graphing Calculator app just by typing it in Google. And so you're going to go to it like this. And then if I hit the little sidebar, I see these points that I labeled right here. So I can just kind of get rid of these, I guess, and go back. And so I can put this whole table in So the first point is 0, 1,000. So input is 0, output is 1,000. And I can see it right here. If you want to, you can click this check mark to label it. The next one is 3, 2,500. Again, I can label it. And you can do the rest of them, but I'm going to just look at 12, 2,800, which is the point that we're interested in. So 12, 2,800. Let's label that. I'm going to get rid of this middle one just to show you guys. I'm going to zoom out a little bit. And if your picture doesn't quite look like this, you can change like the zoom in value by clicking the wrench on the top right. So if I click on that wrench, I see that the X values, so the inputs are going from negative 16.934 to 41.829, and you can change this if you want to make the picture look better. So I can change it from X is 0. I can change it from X is 0 to X is 8 or something like that, and that can make the picture look a little bit better. I can adjust my Y values too, to be like, I don't know, negative 500 to 800. You can mess around with it to get your picture look, or let's do 3,000 actually, to get your picture looking a little bit better. So I'm trying to find the steepness of this line right here, this line segment that joins these two. And so I can use that average rate of change formula. So my starting input is going to be A equals 0. The corresponding output, F of A, is going to be, well, it's going to be 1,000, right? So F of A is 1,000. My B, my ending input is B equals 12, right? Input is always time. And my corresponding output that goes with 12, the termites, is 2,800. Okay, so that's my F of B. Now it's just a matter of plugging this stuff in the formula. So F of B is going to be 2,800 minus F of A, which is 1,000, over B minus A. All right, so 2,800 minus 1,000 is 1,800 divided by 12. Again, on top is our units are termites. On bottom, our unit is month. If we simplify 1,800 divided by 12, well, on top I'm going to get 150 termites per 1 month. So this is a positive average rate of change. So I'm increasing on average in that time frame by 150 termites per 1 month. That's our average rate of change in the whole from 0 to 12. So even though there were parts on this journey where we were losing termites, the net result, the net change, is on average positive 150 termites per 1 month. Okay, so let's do some examples here. Find the average rate of change of this function that they give us on the following intervals. So when we say intervals, we mean the X values, or the independent variable. Okay, so we're starting from 0 to 3. So this is our A and this is our B. And now we want to find the corresponding outputs, F of A and F of B. So if I look at A equals 0, that's right here. That's when X is 0. So when X is 0, and maybe I'll actually write this out a little bit neater. So we have A equals 0. F of 0 is going to be what? Well, we can do it two ways. We can look at the graph, which isn't very helpful because it's a weird point right here that I don't know what that is. So we have a rule that is going to tell us what happens when we plug in 0. So F of 0, and actually our function's called G, so I'm going to use G, right? G of 0 is going to be 0 minus 2 squared plus 3. So again, I'm taking my first input and I'm just plugging it in to see what my corresponding output is going to be. Okay, so that's going to give us, let's see, negative 2 squared plus 3. 4 plus 3 is 7. Okay, so we have A is equal to 0, G of A is equal to 7. Okay, so we need that information here. So our starting input and our starting output. All right, now we need B, so our ending input is 3, right? That's our interval. So now we look at 3, and we can't really see, again, from the graph what that output is going to be. It's not immediately obvious, but we can use our function rule up here to see what happens when I plug in 3 into my function. If I plug in 3 as my input into our function rule, I get 3 minus 2, I'm just plugging in 3 here. I get 3 minus 2 squared plus 3, which is going to give me 1 squared plus 3, which is going to give me 4. Okay, so when B is 3, the corresponding output, G of B, is equal to 4. All right, so now that we have this stuff, we're just going to plug this into our formula. Now, instead of f of b, we're using g of b because that's what my function's name is. So we have g of b minus g of a divided by b minus a. So g of b is 4 minus g of a is 7 over b minus a. So 3 minus 0. That's going to give us negative 3 over 3, which is negative 1. So that is our final answer for A. The steepness of the line segment between 0 and 3 is going to be negative 1. So we're, if you imagine yourself walking, you're walking down. So that's a downward average rate of change. So our answer is negative 1 for part A. What about between negative 1 and positive 4? So between negative 1 and positive 4 is going to be the steepness of that line segment. Oops. So what's the steepness of that line segment? Well, here our starting input is negative 1. Our ending input is 4. Now what is G of negative 1? That's our starting output. Well, again, we're going to just plug in negative 1 into our rule. Our rule is up here. G of negative 1 equals negative 1 minus 2 squared. I'm just plugging in negative 1 in for my input. And then plus 3. So negative 1 minus 2, we have negative 3 squared plus 3, which is going to give us 12. So G of negative 1 is 12. We can do the same thing for our input of 4. So what's G of 4? Well, if I plug in 4 into my rule right here for my input, I get 4 minus 2 squared plus 3. That's going to give us 2 squared plus 3, which is 7. Okay, using my average rate of change formula, I have G of B is 7, right? This is B, G of B is 7. So this is going to give me 7 minus my starting output, which was 12. So 7 minus 12 over B minus A. And so 7 minus 12 is going to give us negative 5. And down here, 4, those double negatives become a positive. So this becomes 4 plus 1 is 5. Negative 5 over 5 is negative 1. So the answer to part B is also negative 1. And notice that kind of makes sense from our picture because the steepness of this line looks to be the steepness of this line, right? So they're going to have the same average rate of change, which is negative 1. All right, what about between A equals 4 and B equals 5? So again, we're thinking X here. Now we're looking at this segment from 4 to 5. And we expect it to be positive, right? Because if I put this guy on here, he's going to be walking up. So here we have A is 4, B is 5. What about G of 4, G of A? Well, we just plug in 4 into our rule. Again, our rule was given in the directions. Input minus 2 squared plus 3. So here our input is 4, so we have 4 minus 2 squared plus 3. That's going to give us 2 squared plus 3, which is 7. Okay. Now what about our ending input 5? Well, what's the corresponding output to 5? If I put in 5 into my rule, I get G of 5 is equal to 5 minus 2 squared plus 3. So this is 3 squared plus 3 is 12. So that's our ending output. So our rate of change formula is going to tell me, G of B, which is 12. So 12 minus G of A, which is 7. All divided by B, which is 5, minus A, which is 4. Simplify the top, I get 5. Simplify the bottom, I get 1. 5 over 1 is 5. So my rate of change from 4 to 5 is going to be 5. And again, we do expect this to be positive because the steepness is moving in a positive direction. We're traveling up a mountain, whereas this guy we're traveling down for the green and the black segment. All right, let's try this. So we're going to find the average rate of change of this function rule between 2 and 4 and between -4 and -2. So again, what they give you when they say interval, they just mean your x value, your A's and B's are your x values, your inputs. So we're starting at A equals 2. So here we have A equals 2, and we have B equals 4. So those are our inputs. And we want to find the corresponding outputs so that we can use our average rate of change formula. And to find those corresponding outputs, we use this function rule. So the first thing says, well, let's figure out what the output for A is. So A is 2, so we're going to plug in 2 into our function rule up here. And f of 2 is going to be 2 squared plus 3 times 2. We're just plugging in 2 whenever we see our input variable. I get 4 plus 6, which is going to give us 10. So f of 2 is 10. Okay, and then we can do the same thing with B. So if I plug in 4 into our rule here, we get f of 4 is equal to 4 squared plus 3 times 4. That's 16 plus 12. And that's going to be 28. All right, so now that we have 1, 2, 3, 4 numbers that we need, we use our average rate of change formula. So f of B, f of our ending value is 28. So 28 minus our starting output value is 10. So 28 minus 10 over B minus A. So 28 minus 10, we have 18 over 2. That's going to simplify to 9. That's our average rate of change. What about -4 and -2? So here our starting value is A equals -4. Our ending input is B equals -2. And to see what f of A is, we're just going to plug in f of -4 into our function rule. So -4 in for x, you get -4 squared plus 3 times -4. And that's going to give us 16 minus 12, which is 4. So f of A is 4. All right, what about B? So f of B is f of -2. We're just plugging in -2 in for the x values into our function rule. So we have -2 squared plus 3 times -2. That's going to give us 4 minus 6, which is -2. All right, so we have all 4 numbers that we need for our formula. So f of b is negative 2 minus f of a is 4, right? F of b, f of a, over b minus a. Okay, b minus a. So on top, we're going to get negative 6. On bottom, these double negatives become a positive. Negative 2, positive 4 makes a positive 2. And finally, negative 6 divided by 2 simplifies to negative 3. So our answer for part B is negative 3. All right, calculate the average rate of change over this interval. Again, when they tell us this just means A and B. So our starting value is going to be, and actually, let's see. Well, yeah, maybe we should switch this because the smaller number usually goes to the left. So maybe we can switch this to negative 1 to 5. Let's go ahead and switch that in the directions. All right, so our starting value, our smallest input is a equals negative 1, so this is a, and our ending input is b equals 5. So we want to know what is f of a and what is f of b so that we can use our formula. So f of a, since a is negative 1, it's just f of negative 1, and we can see what that is from our little table here. When our input is negative 1, our output is 3, so f of negative 1 is 3. Same thing with f of b. Our input is 5, so what is our corresponding output? Well, when x is 5, y is negative 2, so that's our f of b. So now we have all 4 numbers that we need for our average rate of change formula. So our average rate of change formula says f of b, which is negative 2, minus f of a, which is 3, all divided by b minus a. Okay, b minus a. All right, so on top we get negative 5. On bottom we get we get 5, and those two double negatives make a positive, so 5 plus 1 is 6. So our answer here is just negative 5 over 6. That's our average rate of change between a equals negative 1 and b equals 5. All right, let's try this one. We're going to calculate the average rate of change of this function from a equals 1 to b equals 5. So we're thinking of that as our inputs. So between the input of 1 and 5. So here a equals 1 and b equals 5, starting and ending. Now what about f of a? Well, we're just going to plug in 1 into our function rule that they give us up here. So if I plug in 1 into my input, I get 2 to the 1 plus 1, which is 2 to the 2, which is 4. So f of 1 is 4. Okay, so a equals 1, f of a equals 4. Same thing with b. So for f of b, we're going to do, since b is 5, this is f of 5, and we're just going to plug in 5 into our rule up here, in for our input. So we have 2 to the 5 plus 1, which is equal to 2 to the 6, and 2 to the 6 is 64. So that's f of b. So b equals 5, f of b is 64, and now that we have these 4 things, we can put them in our formula for average rate of change. So our average rate of change, we have f of b minus f of a divided by b minus a. And on top we get 60, on bottom we get 4. If we simplify this, we get 15. 60 divided by 4 is 15, and that's our answer. Okay, let's try a word problem here. A ball thrown in the air has a height that's modeled with this function. H of t equals 90t minus 16t squared feet after t seconds. What are the units of measurement for the average rate of change? What does your answer tell you about how to interpret the average rate of change? So this is just a matter of what's the input and what's the output. For the average rate of change, we have the change in output, or the change in y, over the change in input. And our question is, what is the unit for output? What is the unit for input? So the input variable they give us is t. So we know that the units for our input is in seconds. And our output, when we put in t, what are we getting out is h of t. And they tell us that's our height. Okay, so, and our height is in feet. Okay, so our change in output is going to be in feet. Our change in input is going to be in seconds. These are the units, feet per second. So how do we interpret the rate of change? We interpret it in feet per second. This is a measure of speed or velocity, right? How fast something is going. So how fast this ball is traveling is in feet per second. Now let's go ahead and do a problem where we're finding the average rate of change, and we'll interpret it kind of in a real world context here. Let's find the average rate of change between time equals 0 seconds and time equals 2 seconds. So here our starting input is 0 and our ending input is 2. What are the corresponding outputs? So what is f of a, what is f of 0, and what is f of b, f of 2? Well, we just use our rule here, and actually I'm going to use h instead, just because that's our letter here. Our function name is h. So we're going to just use our rule up here to figure out what h of 0 is and what h of 2 is. So h of 0 is going to be, well, we're just going to plug in 0 wherever we see our input variable. So we have 90 times 0 minus 16 times 0 squared. And that's all going to simplify down to 0 when it comes down to it. So h of 0 is 0. H of 2, on the other hand, I'm going to plug in 2 wherever I see an input variable t. So I get 90 times 2 minus 16 times 2 squared. And 90 times 2 is 180 minus 16 times 4. Let's see what this gives us. Is 116. Okay, so h of 2 is 116. And that's all we need to know for the average rate of change formula. Again, if this makes sense to you, great. If you want to see it graphically, you can do that trick that I showed you on Desmos and put in the ordered pairs. This first ordered pair is 0, 0. The second ordered pair is 2, 116. Look at this in Desmos and see, you can look at the line segment and see what's happening. Anyway, let's use our formula. So our formula tells us f of b, which in this case I'm calling h. h of 2 is 116, so ending output minus beginning output is 0. So h of 2 minus h of 0 is 116 minus 0 over b minus a. So 2 minus 0 is 116 over 2, which simplifies down to 58. Now, actually, I'm going to write this down here. So I want my units to be clear. So this is 58 over 1. Because we're in this real-world context, my output units are on top. My output is feet. So this is 58 feet per 1 second. Okay, so outputs on top, feet, inputs on bottom, seconds, feet per second. So this ball is traveling on average 58 feet per second. Okay, what about between t equals 2 and t equals 4? So here our starting input is 2, our ending input is 4, and h of 2 we already computed above. H of 2 was 116. I'm not going to double compute that. But we didn't do h of 4 yet, so let's do that. So this is my scratch work. H of 4, I'm just plugging in 4 into my function rule to get that output here. So 90 times 4 minus 16 times 4 squared. Okay, I'm going to just compute this real quick. Any times 4, we get 360 minus 16 times 16. I'm getting 104. All right, so let's go ahead and calculate the average rate of change with these 4 numbers that we have here. All right, so average rate of change, we have ending output, which is 104. So we have 104 minus starting output, which is 116, over ending input is 4, minus starting input is 2. Now on top are units, remember, are feet, and on bottom are seconds. So 104 minus 116 is minus 12. Feet over 4 minus 2 is 2 seconds. Simplify this even further to get negative 6 feet per second. Now, what do you suppose that means in the real-world context of this problem? Well, a ball is being thrown. So what this means is, because this thing's negative, that means that gravity is taking over and the ball is now falling, as opposed to up here where it was rising in height. Now it's falling because of this negative sign. Okay, so it's going in the opposite direction. All right, use a graph of h to interpret your answers in terms of the motion of the ball. All right, so what I'm going to do is I'm just going to put this function into Desmos. So instead of t, Desmos likes x. So I'm going to put 90x minus 16x squared. This is just our function rule. And notice if I zoom out, I can see this picture. Now I'm going to restrict it. Let me show you how to do this. So all I care about is between between x is 0 and x is 4. So I'm going to restrict it like this. I'm going to put little curly braces by hitting the capital ABC in the bottom left corner. I'm going to find my braces at the bottom of the keyboard like that. And I'm going to put in, I'm going to put in 4. Then I'm going to put this sign, x. I'm going to smash it between 0 and, this should be 0. X is greater than or equal to 0. But at the same time, it's going to be less than or equal to 4, just so I can get the picture that I want. Actually, I should have put this in the top. Sorry. Let's do it up here. So, bigger than 0, smaller than 4. That's how I want to tell the computer to do this. Okay, so that's the part of the picture that I really care about. And, okay, so this is what's happening here. Now, we started between 0 and 2, and we got a positive rate of change, and that makes sense, right? If you were to connect a line segment between 0 and 2, you're going to get, you're going to be walking up, basically. However, between 2 and 4, we noticed that we had a negative rate of change. And that's when the ball is falling between 2 and 4 on average, right? It's still rising up here, but then it starts falling. So on average, it's going to be changing at negative 6 feet per second. So anyway, I didn't really write down what this is, but the idea here is that on average, ball is rising from t equals 0 to t equals 2 and falling from t equals 2 on average to t equals 4. That doesn't mean it's falling the whole time. It just means that on average it's falling. And you guys should try this as an exercise, t equals 1 and t equals 2. Try to find the average rate of change between those t values. Okay. The amount Y in millions of dollars the U.S. Department of Energy spent for research and development from 2005 to 2010 can be approximated by this function right here, between t equals 5 and t equals 10. T represents the year, and we're asked to find the average rate of change from 2005 to 2010, and we want to interpret our answer. Okay. So we just need to know what is our starting input, what is our ending input, which is B, what is our corresponding output with A, and our corresponding output with B. Well, we're trying to figure out from 2005 to 2010. So it says that T represents, T equals 5 represents 2005. So A is going to be 5 and B is going to be 10. That's our starting and ending inputs. Now, what about the corresponding outputs? Well, that is going to be given by my function rule here. So for f of A, I'm just going to be plugging in f of 5 into my function rule. So this is going to be a little bit ugly, but it's okay. So 56.77 times 5 squared minus 366.8 times 5 plus 89.16. I'm just going to compute this. Let's see. Okay, so I'm getting 8501.25. Okay, and then we can do the other one as well. So I'm replacing, instead of 5, I'm replacing it with 10. This is f of 10. So I'm just replacing this with a 10 instead, and I'm evaluating it there. Okay, so I'm getting 109.25. Okay, so that's f of 10. All right, so let's go ahead and use our average rate of change formula. So we have f of B, which is 109.25, minus f of A, which is 8501.25. And what are the units of the top and the bottom? Well, the output is going to be, it says the amount Y in millions of dollars. So this is millions of dollars. And this is going to be over B minus A, which is 10 minus 5. And what are the units here? Well, this is going to be, T represents the years. So this is going to be in years. Okay. All right, so if we do this computation, so let's do 109.25 minus 8501.25. So on top, I'm getting 2423.75 millions of dollars over 5 years. Simplify this even further. To divide 2375 divide by 5, and I'm getting 484.75 millions of dollars per year. That is my average rate of change in this situation. All right, let S of t give the number of acres of wetlands in a state in year t. Assuming that the area goes down over time, what does each statement say about the wetlands? All right, so this is just interpreting what they give us here. So they give us S of 25 minus S of 0. So this is the number of acres in a year t, okay? So 2025, or, well, we don't have to necessarily assume it's 2025, but basically what we have here is S of 25 is going to be the acres of wetland at year 25. Here, this is year 0, so this is like the starting year, right? So this is the acres of wetland at year 0. Okay? And so the difference between those is going to be negative 2,500, right? So we're decreasing over time. So the difference is 2,500, or not 2,500, sorry, 25,000 acres over a period of how many years? Well, this is year 25, this is year 0, so that's a period of 25 years. So it's decreasing. Decreasing. All right, so now we have, this looks suspiciously like the average rate of change formula. And so we want to kind of interpret this in the real world context. So, we have this average rate of change is negative 520. So what is this telling us? Well, if we look at the top, what are the units of the top? Well, the units of the top are in acres, right? S of 20 minus S of 10. So on top we have acres. On bottom we have T is our time. That's going to be in years, acres per year. So acres per year, it's negative 520 acres per 1 year. And so what this is telling us is that we're decreasing on average by 520 acres every year. That is what this is telling us here. So on top we have acres, on bottom we have years, decreasing on average by 520 acres every year. All right, let's check this out. So now we have a savings account balance, and it looks like the way that this person saved is pretty equal every month. That's what this line is telling us here. The first situation we had, this person saving, not so much because the lines kind of varied, like the steepness varied, but this guy is saving in an equal kind of manner. What is the average rate of change between 0 and 3 months? Okay, so from 0 to 3, we can compute this. So first of all, what's A? What's B? What's f of A? What's f of B? We can get this information directly from the graph. Well, the starting input is 0, so that's A, and the ending input is 3, so that's B. And the corresponding output to 0, well, we can look at that graphically. So when our input is 0, our output is 300. So this is 0, 300. So this is going to be 300 right here. And what about our ending output? So when our input is 3, our output is 600. So the ordered pair here is 3, 600. So that is that. Now let's do our rate of change formula. We have f of b, 600, minus f of a, 300, over b minus a. Let's keep our units. Our units on top. So our units here, for our outputs is dollars, and on the bottom our input is months. So when I simplify this thing, I get $300 per 3 months, and if I simplify even further, I get $100 per month. So that's the rate at which the average rate that he's he's saving between months 0 and month 3 is $100 per month. All right, let's check this out. What is the average rate of change between month 0 and month 12? So now we're looking at the big shebang. We're going from month 0, so this is our starting value, month 0, all the way to our ending value, month 12. So our ordered pair here is 12, well, it looks like 1500. So here, our starting value A is 0, 300, or A is 0 and f of A is 300. That's our starting value. And then B, our ending input, is 12, and our ending output is 1500. Now let's use our average rate of change formula. F of B minus f of A over B minus A, and again, this is in dollars per month. Okay, so 1500 minus 300 is 1200 over 12. Compute it. And that's going to just be $100 per month. So what do you notice? Well, it's the same rate of change, right? It's the same steepness. Let me show you what I mean by that. This is a special kind of rate of change that we're going to talk about more next week. But check this out, okay? So for the first scenario, we went from t equals 0 to t equals 3. Okay, so we had this steepness right here. The second scenario, we went from t equals 0 to t equals 12, and the steepness stays the same, right? It doesn't increase or decrease in steepness. So on average, this person saves $100 per month. He doesn't save any more, like the very first example we did, he's constantly saving $100 per month. It's a constant rate of change, as opposed to this first example, he saved, he saved $200 this month, he saved $100 this month, he saved $400 this month, and so forth. That was not a constant rate of change, but this guy is special. This is a constant rate of change here. Okay, so let's do some more examples where we're computing the average rate of change. All right, so here we want to look at the interval from x equals 3 to x equals 12. So here A is going to be 3 and B is going to be 12. Let me actually separate these out. So A is 3, B is 12. And so what is f of A? Well, f of A is f of 3 because A is 3. And f of 3 is going to be 22. So that's 22. F of B is f of 12. And f of 12 is going to be negative 68. So using our formula for average rate of change, so the average rate of change is going to be f of B minus f of A over B minus A. So let's go ahead and compute this and simplify as much as we can. And we get negative 10. We don't have any units here, so our answer is just negative 10. Okay, so now we have a function that's graphed. It says, what is the average rate of change of this function on the interval from negative 6 to negative 3? So here we know that our starting input is negative 6 and our ending input is negative 3. And so what we're trying to do with the rate of change is we're trying to figure out the steepness of the line segment between the point when x is negative 6, so this guy right here, and negative 3, which is right here. So we're trying to figure out the steepness of this segment. Okay, so what is the output value corresponding to A is negative 6? So what is f of a? What is f of negative 6? Well, we can just see that on the graph. That is going to have an output of 0, right? So that's 0. What about f of b? F of b is just f of negative 3. And so what's the output when x is negative 3? Well, that corresponds to a y value of negative 15. So f of b is negative 15. And again, we're just trying to, when we use that average rate of change formula, we're just trying to measure the steepness of this little line segment right here. Okay, so let's go ahead and use our formula. So the average rate of change is going to be f of b minus f of a over b minus a. Okay, on top we get negative 15. On bottom, these double negatives become a positive. Negative 3 plus 6 is going to give us 3. And this is going to simplify down to negative 5. And again, we don't have units here, so our answer is negative 5. And notice this kind of makes sense, because if we were to put someone on this line segment, he would be walking downward from left to right. That's telling us our this function is changing negatively from x equals negative 6 to x equals negative 3. All right, let's do some more real-world problems. It says atmospheric levels of carbon dioxide have risen from 336 parts per million in 1979 to 396 parts per million in 2014. And we want to figure out the average rate of change of the carbon dioxide levels during that time period. All right, so we need to figure out what is A, B, f of A, f of B, all that kind of stuff. So remember that A and B are our inputs, and always, unless stated otherwise, time is going to be our input. So what's our starting time and what's our ending time? Well, typically when they give you years like this, we're not going to use the actual year itself as the time, but we're gonna see how many years pass by to label that as our time. So for instance, our starting value for years is always going to be 0, right? Year 0, which happens to be 1979. And how many years pass by between 1979 and 2014? How many years pass by? Well, 2014 minus 1979. Let's see. Well, that's going to be 35 years. Okay, so we're calling 2014 year 35, and we're calling 1979 year 0. So the math works out. All right, so now we have A and B. Now we need to figure out what is f of A and f of B. All right, so f of A, or f of 0, is going to be the output that corresponds to the input being 0. So what corresponds to 1979 as the output value is 336 parts per million. So this is going to be 336. And what about f of b? So f of b is f of 35, so that's in year 2014. How many parts per million? We have 396 parts per million. So this is 396. Now let's go ahead and compute the average rate of change. So the average rate of change, we have f of b minus f of a. And since this is a real world problem, I'm going to put parts per million on top over, and then b minus a. And this is years. Okay, so, and maybe this will make sense why I said, okay, 1979 is year 0 and 2014 is year 35, so that our units make sense. Okay, so let's go ahead and do this. This is going to be, let's see, 60 on top. Yeah, 60 parts per million on top, and on bottom is 35. Let's go ahead and and simplify this as much as we can. And I'm just going to leave it, well, we can leave it as a decimal. Let's just say this is approximately 1.7 parts per million per year. So that's going to be our average rate of change there with units. Okay, the most freakish change in temperature ever recorded was from -4 degrees to 45 degrees Fahrenheit between 7:30 a.m. and 7:32 a.m. on January 22nd, 1943 in Spearfish, South Dakota. So somewhere this is recorded that this happened. That is kind of freakish, though, because, 2 minutes go by and it's -4 and all of a sudden it's 45 degrees. That's kind of weird, right? What was the average rate of change for this time period? So how much is the temperature changing? Well, we need an A, we need a B, we need an F of A, and we need an F of B. So what do those values correspond to? Well, again, A and B are just our units of time. Now, what do we have here for units of time? Well, we have minutes, right? I mean, that would make sense to put our units of time in minutes because we're going from 7:30 to 7:32. So we were trying to see how the temperature is changing per minute. That makes sense. So, again, we don't want to say that our initial value is 7:30. We want to say that it's at minute 0. And then our final value is at minute 2. Okay? Because 2 minutes pass by from 30 to 32. What about F of A? So what's the temperature at time 0? Well, it goes from -4 degrees Fahrenheit to 45 degrees at 7:32. All right, so now we can find the average rate of change. So average rate of change, we have F of B, so 45 degrees minus -4 degrees over B minus A. All right. So on top, these double negatives make a positive, so that becomes 45 plus 4, which is 49 degrees. And on bottom, 2 minus 0 is 2. Again, our units for the bottom is in minutes. The top is degrees. If we go ahead and divide 49 in half and, do that math, we get 24.5 degrees per 1 minute. That's the average rate of change here. That is pretty crazy. That's how much the temperature increases per minute, is 24.5 degrees Fahrenheit per minute. And it makes sense that this is positive, right? Because we're going from -4, that's our starting value, to 45 degrees. We are expecting that our rate of change is positive. So that was that. And let's go ahead and do one more here. So here we have a graph, and it gives the population of a town in thousands after T years. So the y-axis is population, and the x-axis is years. All right? We want to find the average rate of change during the first 10 years. So we're interested in the first 10 years, so we start at t equals 0, and we end at t equals 10, which is about right here. So we need ordered pairs to correspond with those points. Well, the first ordered pair is at 0, 5. So this is 0, 5. And again, this is t comma f of t. And the second ordered pair is kind of in a weird spot, but we're gonna have to just estimate it. So the x value is 10, or the t value is 10, and the y value appears to be at, I would say that's about 12, because this is 15 right here. I would say that's about 12. So this is at 10 comma 12. This is t f of t. And actually, maybe we can label this as A and B. So our starting input is A, and then our starting output is f of A. And then we have B comma f of B. So let's figure out what the steepness of this line segment is that connects those two. Okay, so let's go ahead and do that. We have f of B, which is 12 minus f of a, which is 5, over b minus a. And we'll include our units here since this is a real world kind of problem. So this is population in thousands. So this is thousands of people. Well, yeah, we're thinking it's people. I mean, it could be the population of dogs or something, but we'll assume it's people. And then on the bottom, this is t years, so this is per year. All right. So this is going to be 7,000 people per 10 years, which is going to reduce, I mean, you know, if we just write this as a decimal, this is just 0.7 thousands of people per year. So that is our average rate of change between year 0 and year 10. All right, does the population of the town grow quicker between year 5 and year 10 or between year 15 and year 30? And explain. So let's just take a gander at the graph, just like an eyeball. Let's see what happens with the steepness of this line segment. So the first line segment that we're concerned with is t equals 5 and t equals 10 line segment. So that is going to be right here. So this is t equals 5 and this is t equals 10. That's that line segment. And we can just connect the dots if we want to, like that. Then the other one is t equals 15 and t equals 30. So that is going to be from t equals 15 to t equals 30. So that's this line segment right here. And the question is, which one grows quicker? Is it this one or this one? Well, to find out which grows quicker, you look at the steepness, right? Which is going to be a harder mountain to climb, this one or this one? Well, it appears that this one is a steeper one, right? So the answer here is between t equals 5 and t equals 10. And you can just answer this and say the line segment that connects the two is steeper than the line segment that connects t equals 15 and t equals 30.